let's talk about chemical equilibrium. That's what this chapter is dedicated to. So before I talk about chemical equilibrium, let me talk about reversible reactions. It turns out that all reactions are reversible. It all depends on the conditions that are employed in order to get the reaction to go in one direction or another. So let's say we have a reaction. Let me go to my, whoops. Let me go to my pen function here. And let me squeeze it over here. Okay, so let's say we have a reaction A plus B to form C, right? Well, it is also possible that C can itself react to form the original reactants A and B, all right? So we call this a reversible reaction. It's reversible because basically the reaction can go both ways, all right? Now, equilibrium is a special situation for a reversible reaction. Basically, at equilibrium, we have a state where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? So basically applying that to this hypothetical situation, as soon as A and B reacts to form C, C immediately forms A and B at the same rate, all right? And that is demonstrated in this graph right here. So this graph is a plot for any reaction pretty much where you have the reaction rate on the y-axis and the time on the x-axis, right? The blue line here represents the formation of the product, right? So of course you'd expect that to naturally increase. And the pink line here represents the rate of disappearance of the reactants, right? And you'll notice that they come together at a certain point where both the rates are equal. And that's basically the equilibrium state. And that basically proceeds for infinity as long as the conditions are the same, all right? So that's basically what makes a reaction achieve a state of dynamic equilibrium, where the rates of the forward and reverse reactions are the same. And one consequence of that is stated down here. The concentrations of the reactants and the products will remain constant pretty much for the rest, for infinity, as I said before, as long as the conditions remain the same, all right? So that's basically what happens when you have a system in a state of dynamic equilibrium. So here's an example of a demonstration of the fact that this type of equilibrium is dynamic. So here we have a situation where we have a saturated solution of sodium chloride, and you have the solid sodium chloride at the bottom of this beaker, right? So basically, let me just write down the equation for what's happening here. So basically, we can represent this using this equation. NaCl solid in equilibrium with NaCl aqueous. All right? So that's basically the equilibrium being set up here. Now, what this person is doing is adding radioactive sodium chloride. In fact, it's a sodium ion that's radioactive to this mixture here, which is already in equilibrium. And then you let it sit for a while. And what you'll find is that the solid radioactive sodium chloride, some of the radioactive sodium will end up in the aqueous part here where you have the aqueous sodium chloride solution, all right? So that basically indicates that it's not a static situation, but a dynamic situation where the radioactive sodium ions, which was in the solid state, will eventually end up in the aqueous state. And some of it will remain in the solid state. So you still have that back and forth taking place between the sodium chloride in the aqueous solution and the sodium chloride in the solid state, right? So as stated here, after a certain time, the solution will contain radioactive sodium ions, and the added salt now contains some stable Na+, all right? Which would be the non-radioactive sodium ions. Okay, so let's try to examine this concept of equilibrium further by looking at a particular reaction. Now, the reaction we'll be looking at here, unfortunately, the equation is not given, so I'm going to write down the equation here. The equation is this: H2 plus I2 in equilibrium with 2HI. So that's a reaction we're looking at here, all right? So you can have the first reaction or the forward reaction where the H2 react with I2 to form HI, and then you can have the reverse reaction where the HI itself reacts to form the H2 and I2. Okay, so what we're going to look at are three experiments which basically represent three different scenarios. The first of which is where you start off with 1.0 m hydrogen iodide and no hydrogen or iodine, right? Maybe I should highlight or point out the fact that the blue line represents the concentration of hydrogen iodide, and the pink line represents the concentrations of both H2 and I2, all right? Okay, so as I was saying, initially you start off with a certain amount of HI and no H2 or I2, and the reaction progresses, which means that the HI will be used up. So, of course, you'd expect that the concentration of the HI will decrease, right? At the same time, you'll have the concentration of the H2 and I2 increase until you get to the point of equilibrium where the rate of the forward and reverse reactions are the same, and therefore the concentrations of H2, I2 will be constant, equal to 0.107 m, and the concentration of the HI will be constant, equal to 0.786, all right? So that's what happened in this case when you start off with 1.0 m of HI and no H2I2. The second experiment is where we start off with 1.0 m each of H2 and I2, right? And no HI. And then again, what happens in this case is that the H2 and I2 will react, so their concentrations will fall. At the same time, HI is being produced, so its concentration will increase. And that those two trends occur and continue until you get to a point of equilibrium where the concentration of H2 and I2 will be constant, equal to 0.213 m, and the concentration of HI also remains constant, equals to 1.573 m, all right? So that's what happens if you start off with 1.0 m of H2 and I2 each and no HI. The third and final experiment is where they start off with 1.0 m each of all the reactants and products, all the components in the system, H2, I2, and HI. And what do we notice in this case? In this case, we notice that the concentration of H2 and I2 falls until it gets to equilibrium, and the concentration of HI rises until you get to equilibrium, all right? So that's basically what happens in the third experiment, all right? So in each case, equilibrium is achieved even though you start off with different amounts of the different components in this equilibrium system. Okay, so this is a table showing you the data based on what we described earlier. So let's see if we can make some sense out of this data. So here we have the initial concentrations for each experiment. Here we have the equilibrium concentrations for each experiment. So what we're going to try to see if there's any mathematical relationship between the equilibrium concentration. So what this person did was say, okay, what we'll do is take the product of H2 and I2 and divide by HI, and let's see what that gets in each case. And we get this number here, this number here, this number here. No real correlation or consistency occurring right there. So the next thing that this person did was multiply the concentration of HI by 2 because you have a coefficient of 2 here. Let's see what that does. Doesn't do anything much. In fact, basically to go from here to here, you divide each of these by 2. And again, you won't get much of a consistency or pattern reflected here. So what this person decided to do next is, instead of multiplying the HI by 2, they raise the concentration of HI by 2, which is a coefficient of HI in the balanced equation. And what do we notice here? We notice that that results in numbers that are very close to each other, almost constant, right? In fact, experimentally speaking, given, limitations and so on, we would regard this as a constant value obtained when you do that calculation for the 3 experiments. So basically, this leads us to what is known as the equilibrium constant expression. In some textbooks, they call it equilibrium law. For a general reaction like this, then the equilibrium expression is given by this. A constant, Kc, right, is equal to the concentration of G, uppercase G, raised to the power of lowercase g, which is the coefficient, times the concentration of uppercase H raised to the coefficient of lowercase h, divided by the concentration of A, uppercase A, raised to the coefficient of lowercase a, and then times the concentration of uppercase B raised to the lower the coefficient of lowercase b. All right. So basically, it's products over reactants. The concentration of the products divided by the concentration of reactants, with each concentration simply raised to the power of its coefficient. Right. So remember now, the products are up top as a numerator, and the reactants are below as a denominator, right? Kc is known as the equilibrium constant, right? Or more specifically, the concentration equilibrium constant, all right? So that's Kc, right? It's a constant based on the data that we saw in that table, right? Remember, well, before we move on to the next line here, I should have started with this first line. The equilibrium constant will be constant regardless of the initial concentration of the reactants and products. And we saw that in the data in the previous slide. Let me just say that at this juncture, and we're going to learn about this later on, that the only factor that affects the actual Kc value is temperature. We're going to say more about that later on. If the temperature changes, then the Kc will change. And later on, we're going to learn how the Kc will change with temperature. All right. Just to remind you that the concentration of the products appear in the numerator, while the concentration of the reactants appear in the denominator, and the exponents to which the concentrations are raised would be the same as the stoichiometric coefficients in the balanced chemical equation. Okay, so let's look at this first example in this chapter. So this question gives you the system of carbon reacting with chlorine to form this compound COCl2. And the question is asking, well, the question says that the equilibrium concentrations of these two compounds, namely COCl2 and Cl2, are the same, right? So the question is asking for you to calculate or find the equilibrium concentration of CO in the reaction. So the first thing I'm going to do is write down the expression for Kc, and that would be concentration of COCl2, which is the reactant. Whoops. I hate when that happens. Kc is equal to the concentration of COCl2, which is the product, divided by the concentration of CO times the concentration of Cl2. All right? Now, the question says that this and this are equal, right? So therefore, we can cancel them out. And this is equal to this number here, which is 1.2 times 10 to the 3, which is the Kc value. So the concentration of CO will be equal to 1 over 1.2 times 10 to the 3, which according to my calculations, 1.2, 1 divided by 1.2 times 10 to the 3 is equal to 8.3 times 10 to the minus 4. All right? So that's a relatively simple example, M. Let me just say something about units, right? Because as you all know, I'm a stickler for units. It turns out that when it comes, the convention, I should say, when it comes to expressions of Kc, we don't use the units. Now, this is a departure of what used to be practiced when I was a student way back in the dark ages. But for some reason, the powers that be have decided that when it comes to equilibrium constants, we do not concern ourselves with the unit, all right? So you'll notice that in this problem and in other problems that you're going to see, units are not really expressed with the Kc values or any other equilibrium constants you're going to meet later on. However, the concentration values must be expressed with their units, so that's the reason why I put the M here, all right? Okay, I'm going to stop here, and the next lecture will deal with modifying chemical equations and see how that affects the corresponding Kc values. Okay, until next time.